Okay. Well, we'll do this part first, and we'll go to the back end. Okay. So we're talking today about another example of a voltaic cell, one that will help you for your quiz, second part of your quiz. As I said before, you guys are going to do the better of the two quizzes. Okay. So I'm going to give you, you're going to get an in-class quiz Monday. That's going to be of the same type. It won't be the same question. It may not be the same stress, but it'll be the same type. It's going to be just like it, but electrodes will be different, the solutions are different, okay, salt bridge is different, okay. You shouldn't have any problem because the concepts are the same, all right? The underlying principles of a battery are all the same, no matter what battery I give you. And this weekend we'll look at a lead acid battery, okay? It's going to have an anode, a cathode, a salt bridge. It's going to have ions moving, okay? And our body creates, as we talked about, a charge. Through our neurons, we set an action potential, a voltage. Now it's a small voltage because if it was a large voltage, okay, we would electrocute ourselves every time we thought about something. Or I move my arms, okay? People who are smart would be like, wouldn't survive, okay? Too much electricity going on. All right, so obviously it's not a big voltage. But the point is, it has everything to do with this application. So I'm going to give you another way to look at voltaic cells and apply a stress to it. So in this example of a voltaic cell, which we can see right now has 0 volts. I know at home you may not be able to see that, but if you play that video, it's 0.00. We have this scenario. Okay, we have a copper electrode and another copper electrode. Well, that's different. We have two of the same metals. And we have a solution here, which is blue, and if you can see, it's made of copper 2 nitrate. By saying copper 2 nitrate is in this solution, what I'm telling you, party people, is that what ions are in the solution? Well, I'm telling you that there is all copper nitrate from table F. Nitrates are always soluble. That Roman numeral 2 is screaming it's a +2 ion. So we have copper +2 in solution, and we have nitrate ions in solution. Just like the test, I expect you to be able to write those ions. Some people forgot the ion in the quiz or test. Same thing, it's a nitrate over here, copper +2. Okay, we're going to have a salt bridge. Right now there's no salt bridge, so that's probably the reason why it's 0 voltage. And we'll see if that's true or not. Okay, we have a salt bridge using a glass tube. By the way, it's filled also with copper nitrate, which means what? There's copper ions and there's nitrate ions. Now, just so happens that the concentrations on both sides are the same as in the salt bridge. They're all coming from this bottle that's 0.1 molar. So every concentration is the same, 0.1 molar for each. Molarity is just a ratio of how much stuff that's dissolved over a somewhat amount of water of solution, or liter of solution. Okay, now we're going to have a voltmeter. It's got a negative part here, positive part here. Okay? We want to make this have positive volts. So I'm going to connect a black lead here. And I'm going to connect a red lead and put that here. Now, I want this reaction to run the forward. Now let's write the reaction. It's kind of weird. Kind of a weird scenario here. If this is a battery that is spontaneous, and I've got this connected to the negative part of the voltmeter, okay, what must this electrode be?
The anode?
Correct. And that's strange, because we know copper is bad at oxidizing. This must be the anode. This is, and that's what, because the anode's negative. This is the positive cathode. Strange. Now, it's not working because there's no salt bridge, right? So let's put a salt bridge in and see if it changes anything. So at some point I'm going to take these guys away. Hey, there I go. And now I'm going to put the salt bridge in. And, oh. What's the voltage if you can't see? 0.00. We've got no voltage. We've got a salt bridge. Anyone guess why there's no voltage? Well, what does no voltage mean? Yes?
Is it because what's in the salt bridge is Cu plus 2 and NO3? It's
Yeah,
already
we have the same amount of copper plus 2 everywhere. That's part of it. We have the same concentration. That actually is the answer. And we have two metals that are the same. And we know that copper plus 2 is good at what? Gaining electrons, but there's nothing in the system that's giving electrons. So this is giving 0 voltage. Think about it. These guys have the same ability to oxidize. These guys have the same ability to reduce. There's not something that's good at pushing and pulling, so it makes sense it's 0. Okay? However, we're going to apply a stress and make this happen. Okay? So we're going to apply a stress to make it go forward. Now, if it does go forward, and it's not, we're at the death of a reaction, right? I know you guys love it. Here's a U diagram. We're at the death of the reaction. That's the equilibrium. We're at 0 volts. I want to force this to go forward to give me some voltage. Okay? Now, if I could, this is what would happen. This copper here would oxidize. It would push some electrons that way, become copper plus 2. This little piggy went to market. No, this copper would gain some electrons. I'm drawing it different just so you can see what happens. And it would plate and become pure copper 0. So this is the reaction. Kind of weird. Copper plus 2 doesn't like to, copper doesn't like to oxidize. How can I force the forward? Okay, to make this do that. If I don't force the forward, we are definitely in equilibrium, death of the process. But I can use Le Chatelier's principle. Okay, and Le Chatelier's principle states, if I apply a stress, the reaction is going to respond. Now, can anyone guess what stress and where that stress will have to be to make the reaction go forward? I want to make this have positive volts. What could I do? I'll tell you what I can't do. I can't change the amount of metal I have, right?
So then
Having more or less metal doesn't change anything because having more metal doesn't increase the way that you would go forward. Having more metal ions doesn't increase the individual ability of copper to oxidize. So it's got to be about the aqueous ions. Ah, if I add more what? Copper plus 2 to what side? If I add, that's this one, right? If I increase the copper plus 2, wouldn't it look to decrease it by shifting away from it? So where would I add the copper plus 2? To the oxidation side. Because if I increase copper plus 2 concentration, the reaction is going to shift to lower copper plus 2. This is the response. So if I increase this, the reaction will shift and make the forward reaction more spontaneous. Okay? Now, what could I do to add it? I could add a common ion. So that's what I do here. Party people, look where I add the common ion. So I'm going to show you the salt I'm going to use here. These are copper ions. Okay, I'm going to bring in here a container. Oh, there it is. I'm going to use copper 2 chloride. What's the charge of copper 2 chloride? Right. That means I'm going to add copper, that's plus 2. Chlorine's negative 1, so how many chlorines do you need? Right. Now, is that aqueous? Well, In table F, chlorine is what? Chlorine is soluble. Where are we soluble? Come on, give it to daddy here. Okay. These guys are soluble. There are some exceptions, like the quiz. And copper is not one of them. Chlorine is soluble. So this is going to break apart into copper plus 2 aqueous plus 2 chloride ions. By adding copper chloride, which is not copper nitrate, we are doing what? Adding a common ion. There's no chlorine here, but there is copper plus 2. So this salt, when it dissolves, if it's soluble, will deliver a copper plus 2. Which means you're going to increase the what? The amount of reactants. We're here. Death of a reaction. What happens? Remember, this is the amount of reactants, 100%. This is product. So if you make more reactants happen, we move this way. We were dead. Now we're here. Now we're going to move toward equilibrium. You have a little bit of a pathway to go forward. We're changing the concentrations. And I think I just did that, didn't I? It's not, again, a credible amount. You're never going to increase this a lot, but I added some solid somewhere. It died pretty quickly. But there it is. For those that can see, that's 0.03. It was 0. We didn't increase it incredibly a lot, 0.3 of a volt, not huge. But we made some spontaneity occur in the forward a little bit by just changing the concentration. Hey, that's how your body creates electrical charge through the axons, called an action potential. If you remember in AP Bio or Bio, what do? We have a sodium-potassium pump who makes an unequal amount of what? Ions inside and outside of the cell membrane of the neuron. By having a pump pumping what? In more potassium than sodium, you have an unequal amount of positives inside the cell. That creates a voltage. That's how it works. So we have a sodium-potassium pump that creates that. We needed me to pour that in. And it goes dead pretty quickly. Has to, because we want to make sure that the nerve can what? Fire again. So it's not going to be tremendous. Okay, so it's important you understand that we create electrical charge by these what we call concentration cells. All right, now, what's another way I can do it? What's another way I can force this to go forward? Because if I click on this, all right, it's going to die pretty quickly. And there's a reason why it dies. See how concentrated this is? This is darker, right? What's diffusion? Diffusion is from what? High concentration source to less. So copper plus 2 is going to be doing what? Diffusing this way. So if I add more ions, it's going to diffuse out. What is really diffusion? High concentration to low. What really is it? If you have something that's highly concentrated, why does it disperse? Things in nature take things that have concentrated source of energy and disperses that. It's called entropy. The reason why something is spontaneous is because you're increasing the entropy of the universe because you're taking a concentrated source, hello, a battery, to a less concentrated source, dead. You learned this in elementary school. You didn't talk about it, though. Hot water or hot goes from what? Hot to cold to hot. Things that are hot have a concentrated source of energy, and they dissipate outward. That's the flow. That's a direction. So having a direction means that we're taking a concentrated source of something and dissipating that energy. Hello? Batteries have concentrated sources of energy. And eventually they do what? They die. Their free energy drops. Okay? We connected to those things. We'll talk more about that. Okay? But in any case, moving on. What did I just add over here? I kind of gave it away. What did I add over here? No one's paying attention. What did I add? Oh, I'm adding what?
Water.
Water. By adding water, aren't I going to dilute the copper plus 2? Right? But I got to add it here. If I lower the copper plus 2, isn't the reaction going to shift to make more of it? Yes. So if I lower the copper plus 2, the reaction is going to shift to make more copper plus 2. But I've got to pour the water in this half cell. Okay? And again, it's not a huge change. I do have to stir a little bit here, but you do get an effect, okay? I needed to add more water there, all right? So adding water, but you have to know which cell there. So that kind of goes over the stresses, okay, how we can make a system that would look like on paper never to work, but by playing God a little bit, by using Le Chatelier's principle and understand what we're doing here. Remember, we're taking, in this case, adding water, what are we doing? We're taking the reactants, okay, we're taking a product away. If you take the product away, you're going to move this way and be more spontaneous. Okay, so this is an example of a concentration cell. Essentially, this is what is in our body. We don't have cathodes and anodes in terms of metals, but we have cell membranes that open up channels for certain ions to flow in and out like a salt bridge. And we have pumps to make different concentrations. I make this more concentrated, that becomes the anode. If I make this more concentrated, this becomes the anode, and electrons will flow the opposite, okay? All right, so let's go take a look at our quiz. The rest of the time, we're just looking at the quiz, so we don't need that, but today was about looking at a concentration cell, all right? And I hope that helped looking at a different system, but uses the same principles.